All right. So now let's look at the other type of improper integral, where the function is unbounded on the integral. And this can happen in a couple of different ways. For example, we could have a function like this. Let's say here's a and here's b. We could have a function that has, say, an asymptote here at a, right? And we want to integrate from a to b. Right? So let's say all of these, in all cases here, the integral a to b of f of x dx could be considered improper. So this is one where it goes off to infinity here. Right? Another one, maybe instead of having the asymptote at a, it could have an asymptote at b. And maybe it goes off to minus infinity. It doesn't have to go to positive infinity. Right? We could have something like that, where this is an asymptote. Right? That's a possibility. And the third possibility for this being an improper integral would be the discontinuity the discontinuity happens somewhere in the middle. So let's say we have c here, and we're looking at a function that was supposed to change. Say we have a function that looks like this. Right? This is another example of when we could have an improper integral here. So what do we do in each of these situations? Oh, and I should point out, we could also have both of these happen at the same time. So we could be infinite going to a and b. Right? So there's lots of options here, but these are sort of the three main types, where either it happens at one end or the other, or possibly both, and then somewhere in the middle. How do we deal with these? Right? So in each case here, so let's call this one case 1, this one case 2, and this one case 3. Right? In case 1, to compute this integral, since the function is going to infinity as we approach a, what we have to do is take a limit as, let's say, c goes to a. In this case, we have to approach from the right-hand side because we're only interested in this part of the function, so we only want to approach from this direction. So as c approaches a from the right, of the integral from c to b, f of x dx. Right? So you can see the theme's kind of the same as when we were doing these infinite intervals. Right? We're just taking limits to these sort of problem areas. Right? In the second example, where it's infinite on the left side, right, instead of doing the limit to a, we have to take a limit as c approaches b, this time from the left. Because again, if we look at our function here, we're integrating from a to b, so we're only interested from the left-hand side here. So this would be from a to c, f of x dx. Right? And finally, the last option we have is, well, what if the discontinuity happens somewhere in the middle? Right? Then, well, much like we had to do with the integral from minus infinity to infinity, we break it into two pieces here. So let's say discontinuity at, I guess I've called this c. Maybe let me change this to a p here, just so I can use c again. So I want to use this value here, p. All right, so discontinuity at x equals p. Then the integral, let me maybe emphasize that p is between these two numbers. All right, then to do this integral, we're again going to split it in two pieces like this. This is supposed to be b. Right, so we split it into two pieces again. So now each of those pieces is one just like this. And so here we could say, well, that first one is the limit as c goes to p from the right. No, from the left, sorry. This one's from the left. Of integral from a to c, f of x dx, plus limit. We should use a different letter here. So let's use k. As k goes to p from the right, of the integral from k to b, f of x dx. All right. So we split it up like that, and it just turns into these simpler integrals again. All right. So as an example of that, I'll just do one example this time to keep it simple here, since they're all kind of based off the same idea. Let's look at the integral from, let's see, from 0 to 1 of, it's a good one, 1 over square root of x dx. Let's say we look at this here. Right? So this integral isn't defined when x equals 0. Or sorry, this function has a discontinuity at x equals 0. So to compute this, we have to take the limit as c approaches 0. Now again here, since that 0 is in the bottom, we have to approach it from the right side of this integral from c to 1 of 1 over square root of x dx. Right? So now let's perform that integral. So c goes to 0 from the right. Integral of 1 over square root of x is going to be 2 square root of x. Right? And that's going to be from c to 1. Right? So if we plug in our bounds here, we're going to get 2 minus 2 square root of c. Right, so we're taking the limit of this as c approaches 0 from the right. So here, it's a good thing that we're taking the limit as we approach 0 from the right, because this isn't defined for negative c values. So that's something you could also run into if you're not careful. Right? But this limit here, since the square root function is continuous up to and including 0, we can just plug that in. So this integral is actually equal to 2. Right? Hopefully that's not too bad. Right, so I think, what are we at? A few minutes? Okay, let's do one more. Let's do one more. Let's look at the example, the integral from 1 to 10 of dx over x minus 2 to the 1/3. Right? So let's look at this. So when computing this integral, right, look at where this function has an issue at. This function has an issue at x equals 2. So we have to split it into two pieces. Right? The part from 1 to 2 and the part from 2 to 10. Okay? So, and to do each of these, we have to take the limit as we approach 2. So here we're going to approach 2 from the left in the first integral. And we're going to approach 2 from the right in the second integral. All right, so let's go ahead and compute these integrals. All right, so if we compute this integral, we're going to, let's see, we're going to have an x minus 2 to the 2/3, because this is negative 1/3 here. And so this is going to be 3/2. right, from 1 to c, plus limit, as k goes to 2 from the right, of, thankfully it's the same integrand, so this is exactly the same. And here this is from k to 10. All right, so let's go ahead and plug in our bounds here so we can take our limits. All right, so plug in the bounds. We have 3 halves c minus 2 to the 2/3. When we plug in 1 here, we're going to get 1 to the 2/3, and that's just 1. So this is minus 3 halves. Plus the limit, this k goes to 2 from the right, of 3 halves x, oh sorry, this will be k minus, nope, this will be 10 first. So this is 8 to the 2/3. So I'll just write it like that. Minus 3 halves. Oops, why did I write 4? Oh, because 8 to the 2/3 is 4. That's why I wrote it. This will be k minus 2 to the 2/3. Right? So we have to figure out what all these values are now. So as c approaches 2 from the left, what is the value of this function? Well, we could always, if we wanted, move over to Mathematica and try and compute that. So let me hope I got the right one here. Cool. So let's go ahead and at least look at the graph of this thing. So let's plot 3 halves x minus 2 to the 2/3. Right? And we're gonna plot that. We really only care about 2 here, so let's look from 1 to 3. All right, just so we can focus on 2. 2 is gonna be right in the middle. All right. Right. So I forgot about something. Mathematica is a bit weird with cube roots. So the way we get around that, okay, there's this function called surd. Is that right? Oh no, sorry. Surd is for the general thing. There's a function, it's called cube root. Sorry, surd is if you want general roots. All right, so it's a bit annoying. If you don't use the cube root function in Mathematica, you only get the positive half. So this is what we're looking at here. Right? So if we look at these values here, it looks like either way we approach this, as we go to 2, this is going to be 0. Right? So it's important to double check these things if you're not 100% sure what your graph is going to look like. All right, so let's go ahead and plug those in. So we're going to have 0 minus 3 halves from the first one. Sorry, back over to the lecture here. Plus, here, again, so the cube root of 8 is 2. 2 squared is 4. So this is 3 halves times 4, which is 6, and then minus 0. So here we're looking at 6 minus 3 halves, which is 4.5, or 9 halves. And that's our answer.